Hi, this is Assignment Experts channel and I am Helen. In this video we are going to discuss Taylor series. Well, it's an expansion of functions into infinite sum of power functions. This series was called in honor of English mathematician Brooke Taylor, though it was known before Taylor's works. But why do we need it? A lot of processes in our world can be described by different functions. Usually, these functions are quite complex. That's why it's difficult or sometimes even impossible to work with them. The problem is greatly simplified if we replace them with simpler functions which resemble our initial complicated function. Polynomials and their properties are well studied, and it's quite easy to deal with them. That's why, from the practical reason, it's very important to find the rule for obtaining polynomials which are close to the value and behavior of real-life function at some neighborhood of the given point. So that's what Taylor series is about, finding sum of polynomials which best fits the function we are interested in. Now let's see how it works. Suppose we want to approximate some function f of x in the vicinity of some point x0. So we need a function which will resemble behavior of our function at some neighborhood of this point. Obviously, at least we can take a constant function. f0 of x equals f of x0. And now our approximation function f_approx of x equals f0 of x. And this is a horizontal straight line. But what about slope of f of x, in other words, the first derivative at the point x0? Obviously, f_approx doesn't approximate that, because f_approx prime of x equals 0 at any point. Look at the graph. F of x is a curve, while f_approx of x is just a horizontal straight line, as you can see. By the way, it's called zero-degree approximation because f0 is the first-degree polynomial function. To construct the function which will approximate f of x along with its first derivative, we should add something to f0, and this addon should be chosen so that it will be equal 0 at the point x0. Let's consider the following addend. f1 of x equals x minus x0 times f prime of x0. And now our approximation function f_approx equals f0 plus f1. Now our approximation function f_approx of x0 equals f of x0. f_approx prime of x0 equals f prime of x0. But f_approx double prime of x equals 0 at any point again. Now we also obtain a straight line, but this time its slope at the point x0 is the same as the slope of our function. But still our approximation is not very good. Let's continue. Now we want to add something to f_approx which will approximate the second derivative of f of x. Let's consider the following term. f2 of x equals x minus x0 squared over 2 times f double prime of x0. As you can see, now along with factor x minus x0 squared appears 1 over 2. That's because when we differentiate its square, 2 appears, and so 1 over 2 multiplied by 2 gives us 1. Now our approximation function equals f0 plus f1 and plus f2. And this approximation is called the second degree approximation function, and this is a parabola. As you can notice, each time we add something to f_approx, which turns into 0 at the point x0. Also has zero derivatives except the highest one it approximates. Particularly, f2 approximates the second derivative. That's why f2 of x0 equals f2 prime of x0 equals 0. But f2 double prime of x0 equals f double prime of x0. The next derivation turns it into 0 again. Thus, we constructed approximation of our function so that it resembles f of x along with its first and second derivative. Look at the graph. Obtained approximation is a parabola. Because here we can see x squared, here we can see x, and those are constants. As you can see, it touches f of x better than previous straight line. In the same manner, we can proceed and construct approximation function, which will approximate f of x along with derivatives of any order. We obtain the series of polynomial functions x minus x0 raised to the nth power. The more terms we add, the better approximation we get. Let function f of x is differentiable in some vicinity of point x0. Then series summing from 0 to infinity the kth derivative of f of x0 over k factorial times x minus x0 raised to the kth power, which is equal to f of x0 plus x minus x0 over 1 factorial times f prime of x0 plus x minus x0 squared over 2 factorial times f double prime of x0 plus and so on, approximates the function f of x in the vicinity of point x0. And this series is called Taylor series of function f of x at the point x0. In case when our point x0 equals 0, we obtain the series summing from 0 to infinity the nth derivative of f of 0 over n factorial times x raised to the nth power. And this is equal to f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus the third derivative of f of 0 over 3 factorial times x cubed plus the fourth derivative of f of 0 over 4 factorial times x raised to the fourth power plus and so on. And this series is called Maclaurin series. So, Maclaurin series is Taylor series of function f of x in the vicinity of point 0. Not for any function Taylor series converges. The idea is that in certain cases, not all the time, you can rewrite your function as an infinite sum of power functions, and you can only do it in some tiny neighborhood of the fixed point of your choice. The ideas discussed above can be summarized by the following theorem. Let our function f of x has n plus 1 derivatives in the vicinity of point x0. Then, if this function can be expanded into series due to powers x minus x0, then this expansion is unique and can be expressed by the following formula. F of x equals summing from 0 to n the kth derivative of f of x0 over k factorial times x minus x0 raised to the kth power plus some remainder term. Remainder term can be represented in different ways. It should be placed if we consider the finite number of terms, because in such case, approximation and our function itself differ. Therefore appears this remainder term. Remainder term thus indicates difference between our function and its approximation by Taylor series. In practice, it's useful to memorize certain expansions of elementary functions. It's like a table of derivatives or integrals. If you have it, you are saving your time in calculations. Now let's consider a couple of examples how to apply Taylor series. We start with exponential function f of x equals exponential of x, and we'll expand this function in the vicinity of point 0. That's why it will be Maclaurin series. First of all, we need to find derivatives of our function. But as we know, the nth derivative of exponential of x equals exponential of x, and at the point 0 that is equal to 1. Let's substitute this into our general formula. Exponential of x equals 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus and so on. Or in complex notation, that is equal to summing from 0 to infinity x raised to the nth power over n factorial, and it holds for any real x. Okay, now to illustrate this formula, let's graph a couple of approximations. Here we can see the graph of our function exponential of x. 0-degree approximation f0 of x equals 1. And this is a horizontal straight line. The first-degree approximation function f1 of x equals 1 plus x. And this is also a straight line. The second-degree approximation function f2 of x equals 1 plus x and plus x squared over 2. And this is a parabola. As you can see, the higher order approximations go closer to the graph of our function. And if we consider infinite number of terms, we'll get exactly the graph of our function exponential of x. Now let's consider logarithmic function f of x equals ln of 1 plus x. Why we are considering logarithm of the argument 1 plus x? That's because we are expanding our function in the vicinity of point 0. And if we consider ln of x, we'll obtain ln of 0, but it doesn't exist. So, first of all, we need to find derivatives of our function. The first derivative of f of x equals 1 over 1 plus x. The second derivative of f of x equals 1 over 1 plus x prime equals minus 1 over 1 plus x squared, and this is equal to minus 1 factorial over 1 plus x squared. The third derivative of our function equals minus 1 factorial over 1 plus x squared prime equals 1 factorial times 2 over 1 plus x cubed, and this equals 2 factorial over 1 plus x cubed. The fourth derivative of f of x equals 2 factorial over 1 plus x cubed prime equals minus 2 factorial times 3 over 1 plus x cubed, and equals minus 3 factorial over 1 plus x, raised to the fourth power. So now we can see a pattern. Sign of derivatives alternates, beginning from plus, then minus, then plus, and so on. And we can write derivatives in the following general form. The nth derivative of f of x equals minus 1 raised to the power n plus 1 times n minus 1 factorial over 1 plus x raised to the nth power. So, as we expanded our function in the vicinity of point 0, we should calculate the value of derivatives at the point 0. And f prime of 0 equals 1. F double prime of 0 equals minus 1 factorial. The third derivative of f of 0 equals 2 factorial. The fourth derivative of our function at the point 0 equals minus 3 factorial. And in general form, we get f, the nth derivative of f of 0 equals minus 1 raised to the power n plus 1 times n minus 1 factorial. Also, we need the value of our function at the point 0. F 0 equals ln of 1 equals 0. Now let's substitute all this stuff into our general formula. And we obtain ln of 1 plus x equals 0 plus 1 over 1 factorial times x minus 1 factorial over 2 factorial times x squared plus 2 factorial over 3 factorial times x cubed minus 3 factorial over 4 factorial times x raised to the fourth power, plus and so on. Or that is equal to x minus x squared over 2 plus x cubed over 3 minus x raised to the fourth power over 4 plus and so on. Or in complex sigma notation, that is equal to summing from 1 to infinity minus 1 raised to the power n plus 1 times x raised to the nth power over n. And it holds for modulus of x less than 1. Now let's consider a couple of approximations of our function. Here we can see the graph of our function logarithm of the argument 1 plus x. The first degree approximation function f1 of x equals x. And this is a straight line. approximation function f2 of x equals x minus x squared over 2. And this is a parabola. Now let's consider the fourth degree approximation function. f4 of x equals x minus x squared over 2 plus x cubed over 3 and minus x raised to the fourth power over 4. And the graph of this function is Now let's consider trigonometric functions, and we start with cosine. First of all, we need to find derivatives of our function. F prime of x equals minus sine of x. F double prime of x equals minus sine of x prime equals minus cosine of x. The third derivative of f of x equals minus cosine x prime equals sine of x. The fourth derivative of f of x equals sine of x prime equals cosine of x. So, on the first step we get our initial function cosine of x, and therefore further we'll get derivatives in the same sequence. Now we should calculate the value of derivatives at the point 0. F prime of 0 equals 0. F double prime of 0 equals negative 1. The third derivative of our function at the point 0 equals 0 again. And the fourth derivative of f of 0 equals 1. So, we have values of derivatives in the following sequence: 0, negative 1, 0, 1, and so on. Hence, odd powers of x are absent because besides them there are zeros. Also, signs in front of even powers alternate, beginning with minus, then plus, then minus, and so on. Also, we need the value of our function at the point 0. F of 0 equals 1. Let's substitute all this stuff into our general formula. Cosine of x equals 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x raised to the fourth power minus 1 over 6 factorial times x raised to the sixth power plus and so on. Or in compact sigma notation, that is equal to summing from 0 to infinity minus 1 raised to the power n times x raised to the power 2n over 2n factorial, and it holds for any real x. Here you can see the graph of our function cosine of x. Let's consider a couple of approximations. f0 of x equals 1, and this is a horizontal straight line. The second degree approximation function f2 of x equals 1 minus x squared over 2, and this is a parabola. The fourth degree approximation function f4 of x equals 1 minus x squared over 2 and plus x raised to the 4th power over 24. And the graph of this function is Now let's consider sine function. The expansion of this function into a Maclaurin series can be found similar to the expansion of cosine function. Here we can see the derivatives of sine of x. On the first step we get our initial function f of x, so therefore further we'll get derivatives in the same sequence. Here we can see the values of our derivatives at the point 0. So we have these values in the following sequence: 1, 0, -1, 0, and so on. Hence even powers of x are absent, because besides them there are zeros. Also signs in front of odd powers alternate, beginning with plus, then minus, then plus, and so on. Here we can see the value of our function at the point 0. Let's substitute all this stuff into our general formula. Sine of x equals 0 plus 1 over 1 factorial times x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x raised to the 5th power minus and so on. Or in compact sigma notation, that is equal to summing from 1 to infinity, -1 raised to the power n plus 1 times x raised to the power 2n minus 1 over 2n minus 1 factorial, and it holds for any real x. Now let's graph a couple of approximations of our function sine of x. Here we can see the graph of our function. The first degree approximation function f1 of x equals x, and this is a straight line. The third degree approximation function f3 of x equals x minus x cubed over 6. And the graph of this function is a cubic parabola. The fifth degree approximation function f5 of x equals x minus x cubed over 6 plus x raised to the 5th power plus 120. And the graph of this function is summing up. Here we can see all the expansions we have considered. These are Maclaurin expansions because they represent functions in the vicinity of point 0. It's useful to memorize them because you'll need these formulas when solving problems. Taylor series allows us to represent a function as a sum of power functions x minus x0 raised to the kth power. Why it is useful? Well, it's often more convenient to operate with them. Later, we'll consider a couple of examples how to apply Taylor series. Thanks for watching us, like our videos and subscribe to our channel. Bye-bye!